question says, what mass of water can be formed from the combustion of 255 grams of methane, CH4, and 325 grams of oxygen, O2? If the actual yield of water is 177 grams, what is the percentage yield? So this is a limiting reagent problem. And if you haven't watched the previous couple of questions, it would be a really good idea to start with those first. But in this case, what we have is we have a mass of methane, this one. Specifically, we have 255 grams of methane. And we have a mass of oxygen, which is 325 grams of oxygen. And we're asked for how much water do we make. We could be asked for how much CO2 do we make, but that's not what it asks. So we have to answer the question that's asked. So it asks us how much water do we make, and then it gives us an actual yield and asks us to find the percent yield. So in order to do this, we actually need to determine the limiting reagent. And the limiting reagent is essentially the chemical you run out of first. So what we have to do is we have to figure out how much water we can make if we use all of our methane, and how much water we can make if we use all of our oxygen. Whichever one is less is clearly going to be the one we make. Why? Because if we use all of this and we run out of it first, we get less water, then we can't make any more water once we run out of this. And conversely, if we run out of this one first, then we can't make any more water because we don't have any more oxygen. So we're going to run out of one of these first. So if we determine how much we can make with all of this and all of this, whichever one is less is the one you're going to run out of first, and therefore is going to be the limiting reagent, and the amount of water you make is going to be the theoretical yield. So in order to do this, unfortunately, it's quite a long job. So what we need to do is we need to convert from methane first, grams of CH4, to moles of CH4, then to moles of water, and then to grams of water. So in the previous question, I talked about grams to moles to moles to grams being very common, because to convert from one thing to another, the units have to be in moles. But conveniently, by convenience, we usually get them in grams. Now, these things are gases, so measuring their grams wouldn't be super convenient. But in a regular reaction where you're measuring, liquids and solids, measuring masses is relatively convenient. So therefore, using grams is easy, but then you have to do the math to convert it to moles. So it's very common, grams to moles to moles to grams. So let's take a look here with methane. We start with 255 grams of CH4 methane. And the reason we know that is that's what it tells us. Now we need to convert it to moles. Well, to convert from grams to moles, we need to use the molar mass. So we need to do a carbon plus 4 hydrogens. And when we do that, we find that the molar mass of methane is 16.05 grams of CH4 is equal to 1 mole of CH4. Now we need to convert from moles of methane to moles of water. To convert from moles of one thing to moles of another, we're always using a balanced chemical equation. In this case, 1 methane gives me 2 water. I want methane to cancel, so I want to put that on the bottom. So I put 1 mole of CH4 on the bottom and 2 moles of H2O on the top. So now I just converted moles of CH4 to moles of water. You'll note that in these plans of attack, every time you have an arrow, you have a conversion factor, right? You need inequality to make it into a conversion factor. Now we want to convert from moles of water to grams of water. That's going to use the molar mass of water, like was done a lot of times in the previous question. 1 mole of water is 18.02 grams of water. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, repeat until the end. And what we find is that if we use all of our methane, we can make 574 to 3 sig figs grams of water. Now what we need to do is we need to figure out how much we can make with all of our oxygen. Note that after we make 574 grams of water, all of our methane is gone. To figure out if our oxygen runs out first, we figure out how much we can make with all of our oxygen and simply see which one is less. So to do that, let's take the same plan of attack, except this time using oxygen. This time we want to start with oxygen and convert grams of oxygen to moles of oxygen, then to moles of water, the same product, and then finally to grams of water. Again, we're finding water, not carbon dioxide, because it asks us what's the mass of water that can be formed. So starting with, in this case, 325 grams of oxygen times we need to convert grams of oxygen to moles of oxygen. Don't forget that oxygen is O2, so don't put in 16, put in 32 grams of oxygen on the bottom and 1 mole of oxygen on the top. Then we need to convert from moles of oxygen to moles of water. Always from moles of one thing to moles of another, balanced chemical equation. In this case, we want to put 2 moles of oxygen on the bottom, because the stoichiometric coefficient is 2, and 2 moles of water on the top, because again, there's a 2 in front of the water. Now, we want to convert from moles of water to grams of water. Note that that's what we did before. So same conversion factor. We put the 1 mole of water on the bottom, just like above, and we put the 18.02 grams of water on the top, again, just like above. So this conversion factor is the same because the conversion's the same. Do all the math, and we find 183 grams of water. So what this means is, if we react all 255 grams of methane, we'll make 574 grams of water. If we react all 325 grams of oxygen, we'll make 183 grams of water. Said another way, after we make 183 grams of water, there's no oxygen left. All right, the oxygen is gone. If the oxygen is gone, we can't make 574 grams of water. We can only make 183 grams of water. This is called the theoretical yield. Okay, because this is the most we can make, because we've run out of oxygen after we make 183 grams. Without any more oxygen, we can't make any more water. Note that it has nothing to do with how much we started with. We actually started with more grams of oxygen, but that many grams of oxygen made less water. So you have to do all this math. You can't just look at these numbers and know which one you're going to run out of first. The last thing we're asked for is the percent yield. And we needed to do all this math to find the percent yield. The percent yield is the actual divided by the theoretical times 100. And of course, it's the actual yield divided by the theoretical yield times 100. So the actual yield in this case is 177 grams. In a lab, you would actually measure the actual yield by putting your product on a balance and measuring it. The theoretical yield is how much we could theoretically get if we used all of our oxygen, and we get 183 grams. Then we multiply that by 100, and we found that this reaction is 96.7% yield. Okay, which is pretty good. In real life, though, I think you'd get closer to 100% yield, and methane would always be the limiting reagent because it's reacting with the oxygen in the air, and usually, you're not going to have enough methane to react all the oxygen in the, in the atmosphere. So, but it gives you a general idea of how this works. These questions are super important. This comes up all the time, and anytime you're doing any type of synthesis thing in a lab, including Gen Chem labs and organic chemistry labs.